So how many of y'all have fallen in love with hierarchical Bayes? No? I have. So anyway, what was neat is you could just watch it from the beginning and you see it just moving towards the, some stable point or stable area, and then it just keeps bouncing around there. So a few things I wanted to go over on it. Most of it is pretty straightforward and there's nothing really to discuss. The answers are on the website now. First of all, why do the means of the B's equal the A's? A is the population mean of your coefficients. A is the population means. And the B's are the coefficients for each person. Okay? If you take the mean of the draws for each person, that gives you the mean of their posterior distribution, the posterior distribution for that person. Then you take a mean of those means, and that gives you the population means. And so if you were doing this exactly correctly and your model, without drawing, that is, if you were actually integrating instead of simulating, and your model was correctly specified, those two would be exactly the same. Okay? And that's kind of a diagnostic test. If they're not, something's going wrong.
It's just an iterated expectation.
Yeah, exactly. Right. It's interesting, though, these are drawn differently. And so just mechanically, you're not forcing that equality. It just occurs. So the mean of the betas, this is the mean beta for person n. That's the our simulated mean of their conditional distribution. You take the average of that over all people, that should equal A. Okay? But the standard deviation of these means is less than D, where D is the population covariance, variance of the coefficients. Why is that? Huh?
Ralph Blackwell. Because the conditional variance is lower than the net conditional. Conditional, well, in a sense you can think about it that way. What were you going to say?
Jensen's inequality.
Let's use real words. I think economists have to learn to get away from using catchphrases and say real words. Say in words why it is that this has to be less than that.
Conditional variance is lower than the unconditional.
Conditioning on what?
That I'm looking at one particular individual. The characteristics of
This is the standard deviation of the coefficients in the population, the true standard deviation. This is the standard deviation of each person's estimate of their coefficients. How come that standard deviation is less? It's not. It's similar to conditioning, but it's not exactly the same.
Because you're taking this. I don't know. The D should be the. Well, you're taking the standard deviation of something that's already an average, so it should have a lower variance than something that's the covariance over
yes.
the N's before their average.
That's one way to think about it. That we've already averaged the B's within each subpopulation, and then we're taking the standard deviation of that over the subpopulations, and that's less than the standard deviation in the population as a whole. That's what you were saying in a yes. The other way to think about it, though, that's also a little bit mechanical. The other way to think about it is what you're doing is you've got some population distribution of coefficients, and the standard deviation of that is captured by D. Okay? And then for each person in your population, you are estimating a conditional distribution for them based on what their choices were. And say we got two people, or let's say this is for one person. With this subpopulation, this conditional distribution is remember what you're doing with this conditioning. If you knew nothing about the person's choices, you would give them the population distribution. And you know more and more about it, it moves towards what their actual coefficients are. And so for any given amount of information you've got about the person, it's kind of, this conditional distribution is somewhere between the population distribution and what their true ones are. You only get partial information about what their true betas are. So let's say this person's true beta is here, true coefficient. If you knew nothing about this person, that would be their conditional distribution, because you're not conditioning on anything. If you condition just a little bit, it moves over towards their true a little bit. A little more, you get more, and eventually it just gets centered right on the true. But for any finite amount of information you've got for that person, you're just moving, you're in a sense averaging. A way to think about this is you're averaging their true coefficient, or your best estimate of their true coefficient, with the population distribution. And so the variance of that is going to be smaller than the variance of the true, because you're always averaging in for each person the population distribution. Essentially, these conditional distributions only move you away from the population distribution to the extent that you've got information about them, about the person's previous choices. And it will only asymptotically move you to the exact true coefficient. So the distribution of these means is going to be, or the variance of these means is going to be less than the variance of the true coefficients themselves. They're not moving the entire direction, the entire amount. Right? This is important. This is extremely important because people misuse these coefficient estimates tremendously. In marketing, people use these means of the population distributions, the conditional distributions, as an indicator of information about that person. And that's doable in the way I described before, that is information. But then if you do that, instead of just for one individual person, you do it for everyone in a sample, it no longer represents the population. It's one of those paradoxical things that using the best information you've got about each person, doing that for an entire population, gives you a worse estimate of the population than ignoring that information about each person. Essentially, you're going to, by using the means of the conditional distributions for everyone in your sample, you're going to underestimate the variety of tastes that are in the population. Because the variety of tastes is actually, this variance in the population is greater than the variance of these means of the conditional distributions. Essentially, it's what you were saying. If we took, we've got lots of conditional distributions here, and if we took the variance over all these conditional distributions rather than over their means, then we'd get the variance of the population back. But we're taking out some of the variance and getting the mean to start with.
To make sure I understood this, it's like saying the variance on a regression line is less than the variance in the original left-hand side.
Yeah, exactly. This is it's a regression towards a mean concept. It's the same idea. It's motivated through different behavior, but yes. Okay, so everything else should have followed through. I want to talk about how hierarchical Bayes and maximum likelihood converge for your estimates. You should realize from last lecture that asymptotically they'll give you the same answer. So if your sample's big enough, you get the same answer on the two of them. There should be no difference at all. In the problem set, we had a relatively large sample, not a large number of people, but a large number of choices for each person. 12, I think we had, wasn't it? And that's quite a bit in a choice situation. And there they converged pretty close. If you looked at it, the mean, the mean, your estimate of the population means, was a little higher using hierarchical Bayes than maximum likelihood. Is that, y'all found that? Yeah. However, when you take that scale factor into account, if you scaled up everything that you get with maximum likelihood, then the two are extremely similar. Okay. There's a paper I did with Joel Huber in which we actually follow this through and do all the comparisons. It's on the website. When you look at the individual betas, the means of the conditional distributions, they're correlated under the two methods at 0.97 or above, depending on which coefficient you're looking at. So really there's this slight scale difference, but other than that, it's, they're very, very similar. Why would you get a scale difference? This is the mean instead of the mode. And maximum likelihood gives you the mode of the distribution, the high point, and hierarchical Bayes gives you the mean. And with a skewed distribution, where the parameters are likely to have a certain sign, then you would expect the mean to be greater than the mode. So what this means is you haven't completely converged. We have still a slightly skewed distribution, so the mean and the mode are not the same. But after we take that difference into account, everything falls into place. So let's see. Oh, and then if you've got a smaller sample such that they're pretty different, suppose you were to do this, normally you wouldn't do both methods because it would be redundant. But if you were to do both methods and got very different answers, what would you say? There's really not much you can say. From a classical perspective, each are equally good. There's no reason to believe one over the other. It all comes down to small sample distributions, sampling distributions in small samples, and we don't know what those are. So they both have the same asymptotic properties. In small samples where the asymptotics don't work, we don't know which one's better. So from a classical perspective, you can't say one's better than the other. You don't know which one to use. If you were a Bayesian, however, from a Bayesian perspective, the hierarchical Bayes procedure is clearly better because you're drawing from the posterior distribution. So you're learning about the posterior, and the posterior is the posterior even in small samples. It's your original information modified by whatever you observe in the sample that gives you your new beliefs. And so from a Bayesian perspective, there would be no, in a small sample, there'd be no reason to use the maximum likelihood. At best, it would just give you an approximation to your posterior. And why do that when you can get your true posterior? Okay. Notice, however, as a result, maximum likelihood procedures are often called approximate Bayesian by the Bayesians. And from a Bayesian perspective, that's true. That's all they are. They give you approximate posteriors, which only converge to the true posterior asymptotically when the two methods converge. So as long as you can get the true posterior, why not do it? From a classical perspective, though, that's a meaningless distinction. Both the posterior and the maximum likelihood distribution that you get are approximations to the true small sample sampling distribution, which is unknown. Okay? And both are approximations that become better and better as sample size rises. So neither is worse than the other. So the idea that one's approximate Bayesian is only relevant if you're trying to estimate the posterior.
So you're in classical?
No, I actually...
No, because you said...
I like both. I really think it's important to keep both in mind, and from my perspective, I'm just pragmatic. I like the ones that are easiest computationally. And so I'll bounce between the two depending on which is easier to do from a mathematical. I still keep interpreting things from a classical perspective, but from a computational perspective, just go between the two. I could imagine a day, though, where I would start thinking, hell, if it's just about as easy to always do hierarchical Bayes, why not just do it and then start, when you don't have a large enough sample, start thinking in Bayesian terms, because there you have precise concepts to use for small samples. So I really think we need to absorb both concepts. So now the question becomes, when is one of these easier than the other? When you ran these models, let me describe what you actually were running here. I'm going to do this model now without time periods just to make the notation easier. What we were running was essentially a model of this form, utility so the coefficients in your model, discrete choice model, are normally distributed with the mean and a covariance in the population. We ran that with a diagonal D and with a full D. Okay? And we did the draws sequentially by drawing, first of all, the coefficients for each person. If this other one works better. Given the population, mean, and standard deviation. And we did this by Metropolis Hastings. And the acceptance so every time we go through, we'd get a new set of coefficients that we call B new. And we accepted them with a probability based on the logit formula of e raised to b nu times your data divided by the sum of that over j. And then the same thing on the bottom with your old value of your coefficients. And then times the probability of the the new, given A and D, and the probability of the old, given A and D. This is the normal distribution there. So we accepted with this as your probability each time around. Remember that? This is important because I'm going to show you how we can change this algorithm very simply to represent non-normal distributions as well. Okay, so we draw beta from that using Metropolis Hastings with that the acceptance rate range. And then try blue. And then we draw the means given the coefficients for each person, where these are distributed normal with a covariance equal to the covariance in the population divided by the number of people, because each of these is a draw from that variant. So B n is the mean of the draws that you got here. And then you draw your covariance matrix given the B's and the A's. Where this is inverted Wishart with degrees of freedom VO, which you set beforehand. We actually set that equal to P, which is the number of parameters or coefficients. Plus N, okay? And V star, where V star is equal to Pi plus the observed covariance in your betas, which you have. If you know the betas and the mean of the betas, then you can calculate a covariance, and that's what this is. And we add to that our prior covariance, and this, of course, becomes less and less important as n rises because this gets bigger and bigger. Okay? So we draw from an inverted Wishart from that, and we just repeat this over and over again. Okay, when you do this with a diagonal D, I've done now experiments on this under a variety of conditions, and the whole point here was to see which one's faster. Because if asymptotically they're the same, and in small samples classicists can't tell which one's better, it really just comes down to which one's faster and more convenient. So what I've been finding is that with a no correlation in coefficients and normal coefficients. Okay, this is equivalent to what your first run was under this problem set compared to what you did with maximum likelihood in problem set number 4. Okay? They're about the same. When you use the same level of accuracy for the two. So use a large number of draws for the Metropolis Hastings for this Gibbs sampling, and in maximum likelihood you use a lot of draws for the from the random coefficients. So they end up about the same speed. If you change things, however, one or the other one becomes relatively easier to do, both from a conceptual point of view and from a computational point of view. What if you change this to full covariance? Normals. Here, what happened when you ran this hierarchical Bayes with full covariance? How much time did it take compared to with the diagonal D? Do you remember? It took about the same amount of time. It really is no harder for it to calculate the full covariance matrix than just the standard deviations of each element. Aside from one step, this procedure from hierarchical Bayes perspective is just as quick as that procedure. However, from maximum likelihood, we didn't even try to estimate this. When I estimated it, it took 260 some odd iterations. You've got 15 extra parameters because of the covariance among these. You have to calculate the gradient with respect to each of those, and then in your iteration, as you got more and more parameters, it's harder to find the maximum because you're maximizing over a larger dimensional likelihood function. So what happens here is maximum likelihood is dominated just radically by the hierarchical Bayes. Hierarchical Bayes ended up taking about a third as much time. Hierarchical Bayes is just about as fast as with the no correlations, and yet maximum likelihood becomes about 3 times slower because of the extra parameters. This gets worse the more coefficients you have. So hierarchical Bayes is much faster. My sense here is if you're ever wanting to do full covariance among your coefficients, you should go hierarchical Bayes. There's really, that dominates so incredibly. And it starts making you think that the only reason we assume a diagonal covariance matrix is to make our maximum likelihood procedure easier to do. We don't really believe these coefficients are uncorrelated. In fact, in our example, the first coefficient was price, and the 5th and 6th ones were time of use rates and seasonal rates. Those practically have to be correlated. If a person cares about price, they're going to care about all 3 of them. So you would expect them to be correlated. So in that case, you have hierarchical Bayes is real good. What if we shift to log normals? With no correlation. Okay. How would we do that? In my program for maximum likelihood, there's an option to put in log normals. You can just do that. Have any of y'all tried to do that? I remember some people emailed me about it. Yeah. Well, if you do it, you'll find that it's hard to. It takes longer to iterate because the likelihood function is not as nicely behaved, and secondly, it really is dependent on getting good starting values. Because if you start in the wrong part of the likelihood function, it'll fail somewhere along the line with maximum likelihood. So here again, maximum likelihood doesn't really work that well because the strange shape of the likelihood function, and getting to the max is difficult to do. What if we were to apply this hierarchical Bayes? Well, we have to adjust this because this is for normals. How would we adjust it for log normals? It turns out that as long as you're staying within distributions that are transformations of normals, it's just a trivial change in this algorithm. In particular, all we have to do is here, instead of putting in the coefficient, put in the exponentiated coefficient. So now our coefficient is equal to the exponentiated value of b plus s eta, where this is now normally distributed. Okay? And so the thing entering the exponential is normally distributed, or actually, to keep this correct, a plus l eta, where L prime is equal to D. Okay? So what you're saying is, now the things that enter here are normally distributed, okay? But the way they enter utility is through a transformation of them. It actually changes nothing here except the utility function that enters your probabilities, the logit model. So now your logit model has exponentiated normally distributed things. As long as you can transform your normal within this logit formula, then these two steps remain the same, and that's what makes this procedure fast. Is these two things are like get done in a second. So as long as you can keep these normal and inverted Wishart, which happens when you have underlying normal terms, then transforming it in the utility function itself only affects this step, which is just a slight arithmetic change. So it ends up that log normals in hierarchical Bayes are just as easy as normal distributions. So again, maximum likelihood here is slower, often doesn't converge, highly dependent on your starting values, and yet hierarchical Bayes is just as easy as otherwise. So if they started out the same, now with log normals, hierarchical Bayes becomes faster. It's not a lot faster. That's not the real advantage. The real advantage is when you're using log normals and maximum likelihood, you might not get a convergence at all, or you have to keep trying new starting values. So that's the problem. Okay, so those makes you think. So if you have log normals with full covariance, you can do that, and so you have correlated log normals. You can have some log normal, some not log normal. Some of them normal and some not log normal by just deciding which ones to exponentiate. Everything's fine. So as long as you're in that group, it seems like hierarchical Bayes is the way to go. What if you want to have some fixed coefficients? This is a situation where, in a sense, the opposite occurs, that maximum likelihood becomes easier and hierarchical Bayes becomes harder. Okay. I'm explaining all this not just to, so you'll have a checklist of what to do when you do it, but so you really think about what it is hierarchical Bayes is doing each time around. Whenever you change something, how does that affect hierarchical Bayes? We understand these ideas easily with maximum likelihood because we've been trained. You've had like 2 courses on this already. But with hierarchical Bayes, it's harder just because it's new to think about how you'd change things. So what if we have fixed coefficients? What do you have to do? For maximum likelihood, you just set one of the standard deviations. If you want one fixed coefficient, you set one of the standard deviations to 0 and keep it at 0. And there's practically no change. You save a little time because you're iterating over fewer parameters. So maximum likelihood is a little bit faster. If you were to do this model here, now I want to change it to be our new model. Suppose we have our new model, which is some fixed parameters f times some variables and some random parameters b. So all I'm doing is now allowing some of the parameters, coefficients, to be fixed. They're the same for all people, and some of them to vary over people. This is often useful. As you see some of my papers, I keep the price coefficient fixed. Paul Rood has talked about how that's a valuable thing to do because of mainly empirical identification. There's just too much varying if you allow all the coefficients to vary. You know, again, I'm not arguing you should do it or not, but if you want to do it, this is how you do it in hierarchical Bayes. So the model just becomes this. Since these are fixed, we can't choose them along with the random coefficients for each person. Why not? Because recall with Metropolis Hastings, you choose a set of coefficients for one person and either accept them or reject them based on the criteria that we developed. If you reject the new ones, you stay with the old ones. That means that some people in your sample have gotten new coefficients and some people are keeping their old coefficients. Well, if F is fixed, you can't have some people in your sample getting the new F and some people getting the old F. So you can't do it within the same step here because that would end up having some people staying with the old F and some people moving to the new F, in which case it's no longer the same for everyone. So you can't do it in this step. So what you do now is condition on the F also and add a new layer of Gibbs sampling. You calculate the varying coefficients based on their mean and standard deviation and the values of the fixed. And then you choose the fixed parameters based on the other things. So you add one new layer of Gibbs sampling on it. Okay, this is what you always do when you can't fit it into your existing layering. You have to add a new layer. Now, when we're choosing the random coefficients for each person, our criterion becomes e raised to f z n I, where this is fixed, plus p nu, b nu, x n I, okay, divided by the sum of that over j. The same f using the old value of the random coefficients for each person. So all we've done here is now we're still choosing the random coefficients, okay, but we're adding to the utility the impact of the fixed coefficient. And we're taking that value as given. So we're not letting it vary from the old to the new. We're just letting the random coefficients vary. And then, if we've got random coefficients for each person, we then do Metropolis Hastings on F for the entire sample. In particular, we now have every person in the sample and put F nu, e raised to the f nu, z n I, plus b in, whatever their values were that we got before, x I n I, divided by the sum of that over j, e f old. Okay. Times a probability if you need it there. We'll, get into the details of it. But here what we're doing is Metropolis Hastings on the fixed coefficient. But since the fixed coefficient is the same for all people, we have to base the criterion of whether to accept a new one or an old one on the probability of each person's observed choices given that f. So essentially we're doing it the probability for each person multiplied by all the people in the sample. But again, it's just an extra Metropolis Hastings step. What that does, however, is double the time. This is the big time sink, these Metropolis Hastings algorithms where you have to calculate this probability for each person. This is extremely quick. Okay? So now what we're doing is Metropolis Hastings twice with calculation of the logit probabilities twice for each person at each iteration. So essentially, by adding a fixed coefficient, we have doubled the amount of time that Metropolis Hastings takes. So what that tells us is in fixed coefficients, maximum likelihood, you reduce your amount of time compared to random. Okay? Whereas for hierarchical Bayes, you double the amount of time. So in this case, maximum likelihood is faster. And then finally, triangular, uniform, other distributions that are not transformations of normals.
There's a problem in the other steps, right?
These two steps are no longer the simple steps that they were. In particular, you will often have to do Metropolis Hastings at these two steps because you end up with a distribution that you're drawing from that is not at all convenient. Okay? And in fact, for triangulars and uniforms, that's what you have to do. You do Metropolis Hastings here too. So that increases the time, whereas for maximum likelihood, there's no difference. You've got the same number of parameters. It's essentially the same. And with triangular and uniforms, experience indicates that it takes as many iterations as for normals. It's quite easy to find the maximum. It's only log normals that really cause the problem. So here, your two easy steps in hierarchical Bayes no longer are easy and become computationally intensive. Okay? Whereas for maximum likelihood, that's not the case. It's just as easy as anything else. So here, maximum likelihood is faster. The point I'm trying to get at is, from a classical perspective, the two are indistinguishable. They're both asymptotically, they converge on each other asymptotically. In small samples, you can't say which one's better. So then what you do is turn to which one's computationally easier to deal with. And there's a realm in which hierarchical Bayes is computationally easier, and there's a realm in which maximum likelihood is computationally easier. You also probably want to take into consideration your own thought process in how hard it is for you to think about how to revise the existing programs to fit your model. Okay. Okay. Is there anything else I want to say about this? Again, if you want a Bayesian perspective, then even if maximum likelihood is faster, you might want to stay with Bayesian because it gives you fully interpretable small sample results. And to tell you the truth, I'm moving that direction. If you add a full covariance to this, fixed coefficients with the normal coefficients being fully correlated, it probably could turn out that hierarchical Bayes is faster because the two balance off each other and you never know where it's going to be. Yeah.
I'm just saying you should add an F to the condition in step 2 and 3. Like
yeah, if you're doing log normals. F actually wouldn't enter these two, though. I mean, it is officially conditioned on it, but it doesn't affect, because when you're drawing the mean of the random coefficients, all you're looking at is what's happening to the random coefficients. Okay? So now what I want to do is kind of like to finish up the course. We've talked about the basic models in and how you use simulation to estimate the more complicated versions of those. But the whole point that I've been trying to emphasize from the beginning is you shouldn't think about having to be restricted to any of these models that we present. What you want to do is, in your situation, come up with what you think the reality of the situation is and apply the kinds of ideas we've used in this class, the different techniques and stuff, to simulate or estimate your own model. So in that regard, what I want to do now is just describe a few more models that you can perhaps use as part of your bag of tricks. So this shows, gives you extra things to use to combine with other things to allow you to deal with your data set and your choice situation. I want to first talk about how to use and combine stated preference data and revealed preference data. This is a big topic that is used in marketing a lot, some in transportation, other fields. What happens if you have ranked data? So instead of just knowing what the person chose, you know what their second choice is, the third choice is, out of the set of alternatives. You don't just know the first choice, which is what they would choose in the real world, but what they think about the other choices. What if you have ordered data? This is different. This is like, you've done a lot of these questionnaire things where they ask you, how much do you like President Bush's performance? And you can give a 1, 2, 3, 4, 5, whatever. For 1 means you really hate it, 5 means you just think it's great. The alternatives are ordered in a natural way, and you'd probably want to incorporate that ordering into your analysis in a succinct fashion. So how do you do that? And then stated valuations. I'll explain what these are. They're used in environmental analysis a lot. And then last, mixed models. Essentially any model that you can write down in closed form, you can then mix it and allow all the parameters to vary in any way you want to. So we've had mixed logit, but that's just one example. Anything you come up with, you could do a mixture on it, and that gives you extra variation and usually more information. So I want to go through each of these. When you come across these in your own data sets, you might want to choose some of these techniques, combine them with other techniques, whatever. Okay, yeah. Oh, there is no lecture next week. We're having the exam next week. So everyone who is not turning in a paper should come for the exam. Yes, it'll just be during class, because it turns out I couldn't find another period where there wasn't conflict with someone. So, is that okay? Good. And when are the papers due? We decided last time. The 18th, Friday the 18th? May. Okay. Okay, stated preference and revealed preference. These are terms that are used a lot. You've probably come across them. Revealed preference is when a person makes a choice. It's data from a situation where a person makes a choice in the real world, in a market situation. A person buys a particular car, for example, and you observe what car they actually purchased. That's called revealed preference because the tastes or the preferences of the person are revealed through their choice. This is the basic concept in microeconomics of people revealing things about their utility function through their actual choices. Stated preference is when you don't observe things from the actual choices, but you ask people hypothetical situations. Essentially, you can offer a person in a survey situation a choice among 4 different cars. So you describe these cars to the person and then ask them, well, if you were offered this choice in the real world, which one would you choose? Okay, so they're not actually buying it. They're just saying which one they would buy in the real world. That's stated preference because they're stating their preferences.
And people are annoyed normally.
They're often annoyed by these questions. Yes. You have to, and that's exactly the idea. When you have these kinds of data, you need to account for various kinds of biases that could occur, and there has been developed a set of techniques for doing that kind of correction. There are advantages and limitations of each, and they kind of complement each other. The basic one is revealed preference is your actual choice. And insofar as people are not self-destructive, they will evidence their own preferences through their choices. They're not going to choose something that's worse than what their preferences would want them to buy, unless they're gaming or self-destructive. So usually this is pretty good information. Stated preference, though, it's not their actual choice. And hence, you're not really sure whether you can trust it. There's a variety of biases that could go on. One is just the irritation. I think there are people who actually sabotage these things because they're just irritated with doing it. Of course, I don't know why they don't just not do it. I refuse to do questionnaires all the time. So, but anyway, there is that. In fact, I was a tutor to an autistic kid a long time ago, and they gave him an IQ test. He made significantly worse than chance, which means he knew the answer and refused to put it down, if you trust the significance of the testing. And I think that's often the case. He was just really upset and didn't like to cooperate with people. And this is a part of autism that I think maybe hasn't been, anyway, I'm not a doctor, I shouldn't say these things, but I thought it was interesting that he did significantly worse than chance. So he's not I mean, that would not be evidence of stupidity. That's evidence of something else. So that could go on. You also have a situation where, you know, in these, you often have people saying they will buy something because they like the concept of themselves buying that. This happens in environmental choices a lot. People will say they do something that's for the environment when in reality they might not. You know, they'd say they'd buy an electric car, but then when it gets down to it, they're still going to buy their SUV and pollute the atmosphere. But they like the idea, oh yeah, I'm that kind of, you know, I'm a real green person. So there's the self-satisfaction issues that go on here. There's also the usually when these are done in person, there's also bias that could be where you're wanting to please the interviewer. The person tries to guess what the interviewer wants you to say, and you say it. You know, so that you'll look good in the eyes of the interviewer. Those are not one and the same thing. The first one is looking good in your own eyes. The other one's looking good in what you think the eyes of the interviewer are. Those are two different kinds of bias. And also, since you're not spending actual money, there's a tendency to overspend in these situations, that you're not actually paying the money for the Maserati, and so you might say you're going to buy it, even though you wouldn't. You know, your spouse will come to the rescue before you actually do that. So in that case, stated preference has a disadvantage. However, there are situations where, you know, revealed preference isn't very good. There's limited variability in your data. For example, if there's everyone faces the same price, or there's a product out there that has attributes and they're all the same for everyone who buys them, you have no variation in your explanatory variables and you can't estimate the model. Or there might be only limited variation, so you can't estimate the model. You can, in stated preference data, you can build into the experiment any amount of variability that you want to. And so often you use stated preference data when the factors that you're interested in don't have sufficient variation in the real world to estimate by revealed preference. Or at an extreme where there's no market data. What if you're wanting to estimate the demand for a new product and it's not out there, and the attributes that you're interested in aren't evidenced in any existing products? Then you can't do it. So what you can do is, in choice experiments, get stated preference data. And of course, you can just build whatever you want to there. For automobiles, we've built hydrogen vehicles and explained them to people and asked them whether they'd buy them and things like that. Of course, the more out from reality you get, the less trustworthy the data you get are. But it's definitely better than nothing, you know, hopefully. And so you combine them. Well, the issue becomes, what if you have both kinds of data? Often you can kind of mitigate each type of data's problems by getting some data on each of the two types. For example, automobiles, you can get stated preference data that gives you more variability in attributes and allows you to consider types of vehicles that aren't out there. And then you get revealed preference data to try to hone in on what the actual choices were and kind of bring it back to reality in a sense. The question becomes then, how do you combine these two types of data? Well, in each of these, you have a utility function that is of this form. Okay? And actually, let me write it out completely. This is the alternative specific constant for alternative I. And beta is actually equal to your original, whatever some underlying parameters might be, divided by lambda, where lambda is the variance of the unobserved factors. Recall from the very beginning that what we're always doing is estimating a scaled model, because scale is not identifiable, such that the error term has some standardized scale, and your parameters then are normalized by the variance of these unincluded factors that enter the error term. And then you've got a constant for each alternative, which captures the unincluded things on average. And this is the average of the unincluded factors. The scaling is by the variance of those unincluded factors. Well, the first thing you'd want to notice is that if you're combining stated preference and reveal preference data, you've got for the same people, same sample, some of each type of data, you would not want to simply stack these observations and do one logit model, or nested logit, or mixed logit, or probit, or whatever you're going to do on the entire set of observations. Because it should be absolutely obvious that the unincluded factors in these two things are radically different. You can't expect them to have the same mean or the variance, because they're two completely different settings. It might be that people respond to horsepower the same in stated preference and reveal preference situations, but the things that are unincluded in the model are all the things that are out there that you didn't measure that affect their choice, and you don't have it in the model. Well, in the real world, there's a ton of things out there. In your stated preference experiment, you describe vehicles to people. Usually you ask the person, now anything that I don't describe, just assume it's the same for all of them. So you're asking them to pretend as if there is no unincluded factors. Now they always will. They'll bring in somehow their own concepts of what the other attributes must be of these vehicles or the choices. But in any case, you'd expect the unincluded factors to be different in these two and the variance of those. And so what you really want to do is to estimate a model in which you have two sets of observations, one for the reveal preference and then one for the stated preference, where these are scaled by some parameter. Okay. So either the stated preference or the reveal preference, you add an extra parameter that scales all the utility to recognize that the error term the unincluded factors for stated preference data have different variance than those for reveal preference data. And you would probably have a separate constant for each alternative to represent the fact that the alternatives have the mean of the unincluded factors is different on each of the two. So you would then include a model which had all your observations, but add in a scale factor for those observations that came from one type of data. Now how do you do this? None of the existing software that's out there allows you to do it. So if you tried to just live on existing software, you wouldn't be able to do this. What you would do is go in and revise the logit code, or any of the codes we've used, to put in a separate scale for a subset of the data. And we did that in our second problem set. Didn't even explain why then, but just did it.
You're missing an X.
Ah, right.
How about the subscript for the returns, right?
IN. Thank you. Or NI, however you want to think about them. Okay. So what you do is put in separate, you have to revise your code. If you're using a code like SST that gives you automatically your alternative specific constants, you would have to create new variables, override that option, create new variables that are just identifiers of the alternative in the data set or alternatives in the other data set, and explicitly enter them, and then put in a scale factor. So this takes care of the fact that there's a lot of factors that are left out that are different in these two, and that affects the scale of your parameters, but it doesn't necessarily affect the ratio. And actually there has been some research on this, not a tremendous amount, but it turns out that people will often overstate their willingness to buy certain kinds of products based on self-image and the interviewer bias, but that the ratio or their willingness to pay, their revealed willingness to pay for attributes of those products is relatively similar in these two. Okay? That the ratio of the elements of beta, after you scale them for the fact that they're at the wrong place, they scale them by a constant and by the scaling factor, end up giving the same ratios as for reveal preference. Why is that? Huh?
The relative preferences?
They're relative preferences. They're ratios of coefficients, which is all that's economically meaningful. The reason I think it happens is because people don't know how to please the interviewer or look good in terms of relative parameters. I mean, you would have to be an econometrician with a computer at your hands while you're answering the questions. to be able to bias your results having to do with these ratios of coefficients. I mean, it would just be, you wouldn't know how to do it. And you kind of know how to, if you're trying to please yourself or please the interviewer, you would say, okay, well, I'm going to buy an electric car more often. And so you just keep saying it. And that would be captured in here. You just push them to a different part of the logit function where they're too high up there on the logit function because of that bias. But in terms of electric cars that have different operating costs versus capital cost, it's very hard for a person to think about how they would bias or evidence particular views about that in their answers. And so there, it's much easier for these to be accurately captured. Yeah?
If you estimate the first equation without the second data, but then you include the second data, then the ratio changes, right? It's something new that's coming, right?
Hopefully they won't change significantly. The idea is that if the ratios of your coefficients are relatively stable with the two data sets, adding the new data won't change them significantly. They might actually change a lot in point estimates, because often the reason you put in stated preference is because there's not enough variation in the reveal preference to get good ratio estimates. And so these could be very imprecise estimates, which means they have huge standard errors on the ratios.
So the advantage is to diminish the standard errors on
Yes.
the thing about.
To diminish the standard errors by putting in data that have more variation, but by taking out the bias that those new data would have insofar as possible. So again, this is just a trick you need to remember. As long as you're writing your own code, it's an extremely easy thing to do. And this is why I've emphasized in this whole class, we're using Gauss, or if you want to use Stata, you write your own code. Don't try to stay dependent on other people's canned programs. This is an extremely useful thing to do. So then you either have a logit model on this or whatever model you want to have after you've added that new thing. Now, ranking data. This is interesting for a variety of purposes. Sometimes when you have stated preference data, you ask people what they like. They will tell you what you could ask them what's your first choice, and then what's your second choice, third choice. If you used only canned programs, you'd be restricted to only looking at their first choice. That's essentially what they chose or would choose in the situation. But often we want to use the information on their second and third choice out of a set of alternatives. That provides us information. It's inefficient to just throw those data away. And there's actually quite easy ways to use this ranked data. If you use it in a logit model, suppose we have three alternatives, A, B, and C, and the person chooses A is best, or no, let's say C is best, A is second best, and B is worst. So that's what you've got. From a logit perspective, you can easily see this as two totally independent observations. The first one is C is chosen from A, B, and C. And then you take out alternative C, and the person now has a choice between A and B, and they choose A from A and B. So if you've got J alternatives that are ranked, you get J minus 1 observations. You can treat these as simply two observations in your estimation data set. The reason you can do this is because, two ways to look at it, the error term is independent over observations in logit, and so knowing that C is best tells you nothing about the relative value of A and B, so this probability does not have to condition on that one. The other way to look at it is the ratio of probabilities by the IIA property is the same whether C is involved or not. So this provides you information on the ratio as much as if C is in there. And that, of course, is the consequence of the independence of the error terms. So here, for each person, you get two pseudo observations from the ranking of your three alternatives. The first one is the probability of of C over, I'll just write it as the, and the next one's going to be The probability of both of these is the product of those, right? Then you take the log of it to enter the likelihood function. The log of a product is just the sum of the logs. And so it ends up being exactly like two separate observations from the data perspective. So the log likelihood then for this person is going to be the log of this if you're using my data, my mixed logit routine, remember it gives you a censoring variable. So essentially you just repeat the observation twice. You have it once and then twice. And in the second time, you censor out whatever was the first choice and leave only the remaining choices. So it's extremely easy to set it up in that data set. In SST, you got to do it more manually. So that's if you want to do logit. Then, of course, you can just do a mixed logit on this by assuming the parameters that enter V are random, and then you take the log likelihood function is the log of the integral of the product of these two probabilities. Times there. The distribution of the betas that enter these V's, UB, and you simulate that just as you would. So this is as if you're having the person in a mixed logit on panel data where they face two different choices. You set up two observations for them, specify the mixed parameters, and just go through it. So mixture of parameters has the advantage of this convenient decomposition that logit has, but it also allows correlation over the two observations because the underlying betas are the same for a given person over those two observations. So it creates correlation, as we've already talked about. What if you wanted to do probit? There is also an extremely easy way to use your existing codes for probit with slight modification to capture ranked data. What we have in this case, if the person was facing three alternatives and made these choices, what that is telling us is that the person is choosing alternative C, thinks that that utility is greater than for alternative A, and then thinks that A is greater than B. This is the information you're getting from the person, that they think utility of alternative C is greater than A is greater than B. We can rewrite this as UA minus UC is less than 0. UB minus UA is less than 0. And if we have utility is equal to bx plus epsilon, this becomes epsilon c a minus epsilon c is less than beta x c minus x a minus c. Differences in utility and differences in error terms. Well, this looks very similar to what we had when we had a multinomial logit, probit, and used GHK to estimate. Okay. Remember there, go back over your notes, you'll remember that we defined this M function that transform your data and your covariance matrix. We can do exactly the same thing as we did there. The steps are exactly the same, except the M matrix is defined differently. Now what we'd have is our M matrix is, remember this is going to be J minus 1 by J. So in this case it's 2 by 3. Okay? And we want this M to be a thing that transforms our original utilities and original data and errors into these differences. So it's going to be 1, 0, negative 1. That gives us A minus C. And it's going to be 0, negative 1, 1, 0. Okay? That takes negative A plus B. So then what we have is, if we have our utilities stacked, so this is A, B, and C, A, B, and C, A, B, and C. What that tells us then is the probability of this person's choices is M times the errors is less than negative M times the x's. Okay? That's exactly what we had with regular GHK use of probit. It's just that M is now defined differently. Yeah?
Don't in the case of probit you have to make an assumption of IA?
Probit? No.
Even when you could imagine a situation where a person given only the choice of A and B would actually rank B preferred to A, when in the case when they're given C, A, and B, they would give the ranking you said. You can imagine a person.
Well, you're getting me confused here, so let's see.
Well, I mean, it's just the IA property, right? Because
that they choose C from A, B, and C, and they choose B
when only A and B are available.
Right.
But I mean, but in the first instance, they could rank them C, A, B in the first choice setting.
Oh.
Yeah, but they
First.
could rank them B, A in the
Second.
second choice setting.
Is
Two Italian restaurants and one Chinese restaurant. So my first choice is Italian, my second choice is Chinese, my third choice is Italian. But when I take out...
Yeah, I see what you're saying. I've gone through that example. Let me get back to this in a second. Let me finish this up the way I think it works, and then we'll see if in fact this works within it. So what you have here then is the probability of the person's ranking is equal to the probability that epsilon star is less than minus bx, let's put these as wiggles, differences, okay, where the variance of epsilon star is equal to m, whatever your original variance was, that, just as we did before with GHK, and x wiggle, I'm getting my notation mixed up here, it's equal to mx, okay? And we feed this, the Cholesky of this into GHK, and we feed this as upper truncation points into GHK, and you use it just as you did before. So if you want to use rank data, all you have to do is use our existing codes, but go in and define M differently to represent the rank orderings. Okay, so now let's get back to your comment.
If this comment is true, that would hold anytime there's sensor data. It doesn't necessarily need to be ranked. I mean, if somebody doesn't have the choice of the Italian restaurant or...
Right. Oh, wait. I see this. We're never using this. We're not doing the trick that you did with Logit, where we take this as the second information. What we're just using is this information. This information tells us when all three alternatives are offered, we think the utility of C is greater than A, and the utility of A is greater than B, when all three alternatives are offered. And each of these, the probability of that ranking is going to depend on the correlation among all the alternatives through this thing. So we actually, I'm glad you did this. This trick that we used in Logit, which is to look at the alternative, take out the first choice and then look at the remaining ones, only works with Logit because of this IIA property. And here when we're doing probit, we're not doing this. There is no probability of B given A and B. This information is what we're using, and that's what we're translating here as utility of C when given all the alternatives is greater than utility of A. Utility of A when given all the alternatives is greater than utility of B. And that can just be reduced into this. I'm glad you asked that. Yeah, because this is a trick that only works with Logit where they're independent. Okay, so this is a probit procedure for using ranked data, and all it takes is a small change in your GHK thing. Now, any questions on this before we go on? I'm actually putting this out now so that you kind of have it in your mind. I don't expect anyone to remember all these details. And if you ever want to do this, you'll remember, oh yeah, there's this procedure that you can use. And then you'll look up my book, which by then will be online, and just find out how to go about doing it. So it's, at this stage, you just kind of have to keep in your mind that these things are available, and they're all slight variations on the code that we've already created. Next, ordered data. Often you'll have data from questionnaires where people are saying how much of something. How true do you think this answer is, or how much do you like this product, 1 to 7. You just did these evaluations. There's like 1 to 7. How much do you like this class? And you want to examine what relates to those responses. So let's suppose we have a situation where you like, how much do you like performance of Bush? And you've got 3 answers that the questionnaire allows you. And you can say 1, 2, or 3. Okay? How would you analyze these data? Now, using the techniques we've got so far, you could actually do it using nested logit or probit. What you want to account for is the fact that neutral, that these things are ordered. That if you take this option out, IIA is not going to hold. It's not that these people are going to shift equally, proportionately to these two. They're probably all going to go to the next lower down. You know, the fact that they're ordered implies there's some kind of substitution factor among them. So there are several things that you could do using our existing models. One is a nested logit, where you could have a choice at the top of 1 versus 1 plus, and then, greater than 1, and then 2 or 3. And there you capture the correlation pattern through a nested logit. If you get more, like a 5-point scale, you can just keep going down further and further. It just gets more complicated. Or you could have a probit. So this is nested logit. Or you could have a probit where these two are correlated and these two are correlated, but these two aren't correlated or have a smaller correlation. Capture the ordered nature in that fashion. It's possible to do that, but that's an example of trying to fit your data into your existing models rather than trying to make your models be accurate representations of your data. What's truly going on here, in each of these, the basic underlying theory is that you've got a utility associated with each option, and maybe that utility is correlated, and we want to capture the correlation. That's not what's happening here. Here you have a unidimensional, there's only one measure here, one utility in a sense. It's a unidimensional concept of how much you like Bush. And this tells you how far up that continuum each person is. So instead of having 3 measures of utility associated with each of these alternatives, which doesn't really make sense, you have one measure, which is the your utility associated with Bush, how much you like Bush. Okay? So one underlying measure. And essentially what it is there's a continuum from negative infinity to positive infinity, and at some break point, the person's going to say, I'm giving an answer of 1 or 2 or 3. So essentially, instead of 3 separate measures that might be correlated, we've got one measure that has breakpoints in it, and where the person falls will determine what answer they give. Okay? So how would we analyze that? What you could do is say that from the researcher's perspective, each person has their own utility, the utility they associate with having President Bush be president, his performance. That's an individual person observes that. They observe their own happiness from having Bush around. Okay? We as researchers observe some factors that relate to that, and we observe some factors that don't relate to that. Okay? So
You don't observe the other ones, right? Epsilons are the unobserved ones.
these are the unobserved things related to how happy that person is with Bush. Okay? Then we make a distributional assumption on these unobserved things. This is just within our tradition, but now we're recognizing the fact that these are ordered and actually reflects one underlying measure. So we say that, say, this is logistic. A logistic is the difference between two extreme values, and it gives you your nice S-shaped logic curve. Or you could say it's standard normal. You want to set the variance of this, whatever it is, to set scale, because obviously utility has no scale. Okay? And then, given this underlying thing, you want to know what's the probability of a person's answer. So let's say the person said 3, or let's say 1. The probability of a 1 is simply equal to, let's say this is logistic, okay? It's going to be E beta x n over 1 plus E beta x n. That's the probability. What we have is a distribution. Okay? It's the probability that this is going to be below A. I'm sorry. Getting this wrong here. A minus this. Okay. So it's essentially the cumulative probability up to that. Or another way to put it, it's the probability that your measure is below A. What's the probability of giving an answer of 2? It's the probability that you're going to be between A and B somewhere. So it's B minus beta xn over 1 plus E beta xn. That's the cumulative up to here. And subtract out the cumulative up to A because they didn't give an answer of 1. Okay. Now what you're estimating is the coefficients of your explanatory variables. We've got to stop. Okay. So now what we're estimating is we're estimating the coefficients of the parameters which affect the mean of their distribution, and B and A. Okay, and the cutoff points. So essentially we're estimating factors that relate to how much a person likes Bush that you can observe, and then the cutoff points for when a 1 becomes a 2 and a 2 becomes a 3. Okay? This is much more related to what the actual data are. It's the idea that you've got some underlying happiness associated with this president, and when it reaches a certain threshold, you say, well, I like it, or I don't like it, if it doesn't reach that threshold. And we estimate those thresholds as well as the factors that you observe that go to the data. This you have to write your own code for, but as you can see, it's not very difficult. You just have different functions of logits. They're all closed form. So the log likelihood for a person that chose alternative 2 would simply be the log of these two logit functions. And so the log, instead of a log of one logit, it's the log of the difference between two logits. And you just code that in. And then if you want to mix it, so the betas are random, or even the A and B are random, you just integrate this over those random coefficients, and you don't have any extra difficulty. Okay. You can do this with a probit model by just having this be, instead of logistic, have it be normal. And in fact, if you've got several answers, you know, you ask a question, how much do you like Bush? And then you ask a question of, to what extent do you think immigrants should be allowed to have free hospital care? You know, people who like Bush probably would say they don't think they should get free hospital care. And the two are correlated in unobserved factors. You can get that incorporated also. Yeah?
With this, you still have the assumption that all the betas are the same across the groups, correct?
In the setup I've got here, but then if you wanted to get rid of that, you would just take this probability, integrate it over random betas to get a mixed version of this. Is that what you're, yeah. So you could allow that and estimate the distribution of these betas. Anything we write a closed form for given parameters, you can then mix it by letting those parameters be random. Okay, stated valuation. This is another kind of data that you might come across. It's used in environmental a lot, and it's very similar to these data eventually you see how it becomes related. Essentially what goes on here is you have a questionnaire in which you ask people how much are you willing to pay for something. For example, for the Alaska oil slicks from Exxon Valdez, the question they ask people is how much would you be willing to pay to contribute towards a fund that will clean off the birds that have been slicked? Or how much would you be willing to pay to prevent that type of slicking to occur in the future? And instead of just asking it open-ended, because people have found in these studies that the respondent really has no idea how to answer, they usually ask it kind of like, well, would you be willing to pay $50 to have this happen? And if the person says yes, then you up it and say, well, would you be willing to pay $75? Okay? And either stop then or just continue until you kind of get a limit on how much they're willing to pay. If they say, no, I'm not willing to pay $50, then you say, well, are you willing to pay $25 or $10 or something, and continue down in that path. What that ends up giving you is essentially the same kind of information here that you can analyze in essentially the same kind of way. What you've got is a true willingness to pay. And we ask the person questions like, are you willing to pay $50? If the person says no, then the subsequent question is, are you willing to pay $25? If they say no to this question and yes to this question, that means they're in this range. So that's equivalent to that person getting a 2. Okay? If they say, yes, I'm willing to pay $50, and then you up it in the next question to 75, and they say, well, no, I'm not willing to pay 75, that tells you they're in this range. Okay? If they say, yes, I'm willing to pay 75, and you don't ask any subsequent questions, that tells you you're in this range. So by asking these questions, you're essentially dividing the willingness to pay range into categories and finding out which category the person fits in. This is formally equivalent to these ordered data that we were describing, except that now the cut points, instead of being estimated, become fixed by the experiment, okay? Or given by the experiment. And so what you end up having again is that a person who said no to this question and yes to this question will have 50 here and 25 here, etc. So the A and B are no longer estimated but are given by the experimental design. But otherwise it's exactly the same. Probability of being in this range is the cumulative probability of your error terms bringing you up to here minus the cumulative probability that they bring you up here. So willingness to pay is equal to some observed factors and unobserved factors, and there's a distribution on this which gives you rise to your probabilities. And then of course you can mix it just like anything else. Yeah?
How do you know you're going to have fast attendance? If I start out with 50 and go on, I might get much different results than I start with
Yes, I described this as if you were taking the data as truly meaningful, that the person is answering their correctly. What has been found, though, Dan McFadden's done a lot of work on this, where there is a tremendous amount of not only path dependence, but what he's calling anchoring. If you start with 500 instead of 50, you will get higher willingness to pay. Now, if people were answering truthfully, that wouldn't be the case. You'd get the same distribution of willingness to pay no matter where you started. But by where you start the questioning really determines a lot. Also, the sequencing determines, and that's what you were talking about, path dependence. What I found here is that usually the people will answer yes and then followed by a no. So they immediately get the next one's a no. Or they answer yes and you immediately get a no. So wherever you start, you get people in either of the two groups on each side. You very seldom get them over here or over here. And I think what's psychologically going on there is the person, again, is trying to figure out what in the hell is the interviewer wanting here, or what's meaningful. You say, yes, I'm willing to pay 50, and the guy asks you 75. Well, you know, I know where this game's going. You know, and you quit. You say, no, I'm not willing to pay. I said 50. You know, or you say 50, no, I'm not willing to pay, and the person says, well, how about 25? And you think they're saying, reproaching you for being such a cheapskate. Well, how about 25? And so you say yes. You know, you're not paying the money. And so you get these problems. This is a problem with the data collection. It's, I don't think, amenable to modeling. It's how you interpret your data and stuff. I don't know if there are ways to get around. After you've collected your data, correct it through the modeling. There might be. But what I was talking about is if you take your data at face value, how do you analyze it correctly? What would be worse is to take these data and then add on top of it a procedure that doesn't even relate to the process you're looking at. So going on here.
So they would not ask, like, already since the start, give them the intervals.
Where are you in the thing?
They don't do that.
Whatever ways have been tried, my view here is whatever ways have been tried here have failed in various ways. And the problem is very basic. The person answering the question doesn't know what it means.
But because if you ask the first question, you're already, why did he say 50, right?
Right. You're asking, what does...
You just give him the interval, let them choose.
Yeah, but what does that really mean? I mean, I think... You got two problems going on here. I'm sorry?
They'll still look at what the divisions are. If they're $5 divisions or $100 divisions or $25.
And if you give the whole range up to 25,000, I got a letter recently from Harvard asking me if I'd like to contribute. You know, now that you're old and hopefully senile, you might might be willing to give money. And they said to check off how much you're willing to give. The first box was 10,000. Give me a break. I just threw it away. Even though the very last, you know. If the last box was $25, you know, but here they gave the whole range, and you know, anyway.
And they suggested 10,000 first.
Right, they put the 10,000 first. I figured, you know, if they're talking to people that rich, they don't need my money. And so you infer things about who's sending it and all this stuff from it. You don't, you know, and the problem with these kinds of questions is you've got the free rider problem. Why should I spend my money? If it's actually going to happen, it'll happen without my money. Or if it's not going to happen, why should I give my money at all? You know, why should I contribute $50 if the oil slick birds are still going to be slicked? Because you know your 50 is not going to cure the problem. So you get, this is a fundamental conceptual problem in these kinds of issues that I don't think any way of asking the question is going to get around. But if you've got these data, this is done a lot in environmental analysis. It's better to do it this way than try to fit it some other kind of model. One thing that is interesting in this regard is that when these things were done, one group did a study about how much you'd be willing to pay for 1,000 birds to be saved versus 10,000 versus 2 million. They got the same answer, which are the same average willingness to pay, which can't be used legally because damages legally have to be related to the extent of the damage. You can't have dollar damages unrelated to the harm that's done. And here, the amount of harm is unrelated to the dollar damages. But it also makes you wonder whether people are just, again, responding to the questionnaire versus the actual harm. I don't know. Or maybe 2 million birds is worth 10,000 birds. I mean, that's the people have argued, but I don't know. Okay, we were getting far afield here, but the idea is you get your data in a particular form and try to get your model to represent your data collection and behavioral procedure, even if that entails changing the codes that you've got. And then last, mixed models. I've already said everything that really needs to be said. Anything you can write in a closed form as a function of parameters, you can then make an integral of those parameters over a distribution. So you can mix it and allow a lot more flexibility. You can, we've done mixed logit. We also estimated nested logits. Nested logits are a good way to get a particular kind of correlation pattern between alternatives. You can do that in a mixed logit, but you have to add extra mixing terms. You have to add variables that have random coefficients to allow that. With a nested model, it's incorporated in the closed form itself. So then you can do a mixed nested logit, where the correlations across alternatives are captured through the nested logit in closed form, and then the parameters of, say, the price coefficient and other coefficients vary in the population to give you the mixture. So that way, you're kind of exploiting the advantage of both. You're getting closed form to capture as much as you can, and then the mixture to capture the remainder. So even though you can do it in a mixed logit, doing it in a nested logit is useful. Also, what if you want to do a probit model? So you've got your basic utility, where your errors are distributed normal, 0, omega. Okay. If this were normal, if you want to have your coefficients be random, if this is normal, then you just translate it into their means plus deviations from the means. And now this thing is all normal with a covariance structure that it depends on the ends. You estimate that by GHK, exactly the same. You just have a different covariance matrix for each person. Our code already takes one person at a time in GHK, so you just make the covariance matrix for these normals depend on the data. That's no problem. So as long as it's normal, then use GHK. And we really don't have, that's just a pure probit. Now, what if we wanted some of these to be log normal? Or some other distribution, uniform, triangular, or something like that. Then you can't use this thing of taking the deviations into the error term, and since you got normals plus normals, it all ends up being normal, because some of them aren't normal. So you can't use GHK exclusively. Here, what you can do easily, conceptually, it'll take a lot of computer time, but you do a mixture of probits. You first draw your non-normally distributed coefficients, say your log normals, set those, and then for that draw, calculate the probability of their choice from GHK, knowing that all the remaining terms are normal. So the non-normal terms you draw, and then for each draw of those, you calculate the probability based on GHK. So this is like doing a mixed logit, but instead of having your logit formula as the kernel, you have your GHK probability as the kernel. And each time you calculate that, you have to call the GHK simulator. Again, it takes very little change in the code. The problem, of course, is for each draw of your non-normal coefficients, you're going to have to do a GHK calculation. So this will take a tremendous amount of time. But it's doable. You just turn it on and let it go for a week. And this is useful because, as you recall, mixed logit itself has a very hard time capturing just pure covariance terms. Okay? And if that's what you're wanting to do, have pure covariance terms in addition to random coefficients that aren't normal, then a mixed probit using this mixture of GHK probabilities is a way to go. Okay, so this is how you think about your modeling and add them all together. like I said, I enjoyed this course. I appreciate all of y'all coming, and I'll see some of you next week for the exam. Thank you. Thank you.